Good day. This is 300 Plus Academy, where all we do is exams tutoring, helping you to ace your next exams. Okay, still on the subject matter GCE, alternative to practical physics, electricity. We have another probable question for you, another experiment. Recall we said that for alternative to practical, the experiment had actually been performed on your behalf just for you to take readings, evaluate data, plot graph, and answer questions that ensue. So what do we have today? It's still on an AC circuit with variable low voltage. We have a voltmeter there, we have an ammeter there. Okay, in this particular experiment, we're looking at a circuit diagram showing a solenoid and an ammeter connected in series with an alternating current source of variable voltage. Let's leave the stories. What matters is we want to take, we want to interpret, we want to take figures, we want to come out with figures in a table so that we can plot our graph. So the very first question for this experiment is that we should read and record the values of the current I. That we have already done. If you look at figure 3A, 0 to 1 to 2 to 3, if you read that from I1, I2, I3, I4, I5 representing serial number 1 to 5, for the current you have 0.25, 0.75, 1.30, 1.80, and 2.50. For the voltage, we look at figure 3B in volts, 0, 10, 20, 30. If we look at where the figure points to for V1, that is actually the 2 volt mark. For serial number 2, that's V2, it points at the 6.00 mark. For the third one, it points at the 10.00 voltage mark, and the fourth one 14 volts, the fifth one 20 volts. That is on question Roman figure 1 and Roman figure 2, as you can see on your screen. Read and record the values of I of the current. For the second one, read and record the corresponding values V of the voltage. For Roman figure 3, we were told to evaluate the inverse of the current and also the inverse of the voltage. Looking at this, one inverse of the current means 1 over I, and that makes the unit to become per ampere. 1 divided by 0.25, that is 4. 1 divided by 0.75, that is 1.33. 1 divided by 1.30, that is 0.77 to 2 decimal place. 1 divided by 1.80, that's 0.56. 1 divided by 2.50, that is 0.40. Okay. Here we have, for the voltage, inverse of the voltage, that's going to be 1 over V. And what you have here is 1 divided by 2, 0.50. 1 divided by 6, 0.17. 1 divided by 10, 0.10 per volt. 1 divided by 14, 0.07 per volt. 1 divided by 20, 0.05 per volt. So that ends question Roman figure 3. We've been able to evaluate the inverse of the current and then the inverse of the voltage. For Roman figure 4, we're told to tabulate our readings. Tabulating that we've done already. So this covers questions from Roman figure 1 to Roman figure 4. So for Roman figure 5, we were told to plot our graph. We are plotting a graph of e raised to power minus 1 on the vertical axis. For Roman figure 5, plots a graph of e raised to power minus 1 per volt against I raised to power minus 1 per ampere. So doing that, the first thing to do, like I always say, is to write your exact title: graph of V raised to power minus 1 in per volts against I raised to power minus 1 in per ampere. So once you've done that, the next thing you need to do is to, of course, rule a line for your vertical axis and indicate what is to be on the vertical axis: V raised to power minus 1 per volt. And on the horizontal axis, you're drawing a line for that as well. This is going to be I raised to power minus 1 in per amperes. So once you've done that, the next thing you want to do is to pick your point. Okay, for this particular graph, okay, the least value for my voltage is 0.05 and the highest is 0.5. So I'm trying to figure out what that is going to look like. I am thinking of using 0.05, 0.05, and then 0.1, 0.15, 0.2, 0.25, 0.3, 0.35. Okay, this is not going to get me to what I want, so I'd rather go for 0.1, 0.1, 0.2, 0.3, 0.4, 0.5. But of course, on a paper graph, you could go more than that. You could go more than that because it's a lot. It has the length is more. The length is more on paper. So I'm going to take this as 0.10, 0.20, 0.30, 0.40, 0.50, 0.50. Of course, that just does it. And then we're going to have for the horizontal axis, you're looking at 0.40 to 4. So I'm just going to think 1, 2, 3, 4. Of course, I think I can do that. Yes, I'm looking at 1 to 4. So I'm thinking, okay, let's look at that. 1, 2, 3, and then 4. So that what that means is 1.00, 2.00, 3.00, and then 4.00. Okay, so that's exactly what we have for this 4.00. Okay, now to pick up our points now, when the current was 4, the voltage was 0.5. Yes, so 0.5 and then 4. So that's this point. We get that out of the way. So the next thing is when the voltage is 0.17, 0.17, we can see that 10, 1, 2, 3, 4, 5, 6, 7, 0.17 and 1.33. This is 1.1, 1.2, 1.3, 33 should be somewhere here. 33 should be somewhere here. So, and 1.33 and 0.17. If I chase that, that is looking here. So I'm going to get that as well, so that it's looking like, okay, it's going to go this way. Yes, let's see how it goes. Okay, now 0.10 and 0.77. This is 0.10. 0.77 is going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Of course, 7, this is 8. 7 should be somewhere here. So if I am to trace that, I should be looking at somewhere here, and that just does it. So 0.07 for my voltage and 0.56 for my current. 0.07. This is 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, and 0.56. This is 0.07 and 0.56, 0.1, 0.2, 0.3, 0.4, 0.5 should be somewhere around here. Okay, if I trace that, yes, that just does it. So, and lastly, I have 0.05 and 0.40. 0.05 on the vertical axis, 0.01, 0.02, 0.03, 0.04, 0.05, and 0.40, 0.1, 0.2, 0.3, 0.4. That should be here. Here. That should be here. That should be here. So, and that way I've been able to get my 5 points to gather, and that is for plotting of my graph on Roman figure 5. I've done that. Now on Roman figure 6, I was told to determine the slope. I was told to determine the slope for this graph. So to get my slope, that's lest I forget, let me talk about my scale. I don't want to forget my scale this time. Okay. If you look at what I did here, I used 2 centimeters to represent 0.10 units. But on paper, because the length is more, you can as well use 4 centimeters to represent 0.10 units. And you're going to have a very fine graph that way. But this way, what I have here is from here to here is 2 centimeters, from here to here is 2 centimeters. So on my voltage axis, on V raised to power minus 1 in per volts, I should be saying 2 centimeters. That's 2 centimeters to represent 0.10 per volt. But when you are dealing with it on paper, I would suggest you use 4 centimeters from here to here, to represent 0.10 unit. That way you're going to have a very beautiful graph. Okay, on the inverse of the current axis, that's on the horizontal axis in per amps. Okay, I am using, look at it, from here to here is 2, and from here to here is 2. So that's 4 centimeters to represent 1 per ampere. So that is my scale for this graph. And the next thing, okay, for question number VI is for me to get the slope of this graph. In trying to get the slope of this graph, I'll try to see if I can pick all the points together. Yes, it looks feasible. It looks feasible. Okay. Okay. Oh well. At least I'm able to get 4 points. I'm able to get 4 points together. So, or should I use a red marker? Okay, let me try that. And it goes right to the origin. Okay, so, and that's exactly what I have there. That's exactly what I have there. It looks pretty manageable. Like I always say, it is a lot more easier when you're plotting on paper as against when you're plotting on a whiteboard. Okay, now let's get the slope proper. Okay, I'm gonna pick my ruler to get the point I am comfortable dealing with. Okay. I'm comfortable dealing with this. Should I? Okay, I just want to stop here. Yes, let me make my extrapolation and get that once and for all. Okay, so this is my change in volt per volt, and this here is my change in the inverse of the current. So this here is going to represent my slope. So what this means, if I make my extrapolation, in order to get the position of my, okay, this looks like my y2, my y1. Okay, this looks like my x here, x1, and this here looks like my x2. Okay, so that for the slope you're telling me to VI, you're telling me to calculate the slope. For the slope you're telling me to calculate here, that is change in the inverse of the voltage in per volt divided by change in inverse of the current in per ampere. So what I have here, if you look at it, that's 0.50. 0.50, take out 0.20 all in per volt divided by, of course, my x2 here. That is, if I'm to look at it very well, this is 3. It ends on 0.4. It ends on 4. So what I have is 4.00. Take out, this is 1. This is 1.5. 1.6. 1.6. So if I compute this means 0.30 per volt divided by 4, take out 2.60, that is 2.40 per ampere. Let me quickly compute that. 0.30 divided by, a minute please, 0.30 divided by 2.40, that is 0.125. That's 0.125. But of course, recall I told you about this unit, 1 over V times ampere over 1. So that gives 0.125 ampere per volt, which is the same thing as saying 0.125 per ohm. So this represents my slope. Okay, moving on to question VII7. Haven't determined the value for our slope, as you can see here. Haven't determined that. Moving on to question VII. I was told to determine the current when V is 8 volts. Of course, we did not deal in volts, so it is only correct that if we can convert this to the inverse of the inverse of the voltage, that's going to be 1 over 8. 1 over 8, if we compute that, that is going to be 0.125 per volt. So we then see our graph. Then try to locate that on our graph. 0.125 per volt corresponds to what? Let's try to look at that. This is 0.10, 0.11, 0.11, 0.12, 0.125 should be somewhere here. 0.125 should be somewhere here. So that I am going to trace using my ruler. That I'm going to trace. Of course, I'm using a whiteboard, so the discrepancies will be there. Okay, so I'm going to trace that. This is 0.125. Tracing that down, it falls on 1. It falls on 1, and that corresponds to 1.00 per ampere. But I was told to look for I, not the inverse. So my I is going to be 1 divided by 1. So 1 divided by 1 per ampere is still going to give me 1 ampere. So what that means is that when my voltage is 8, my ammeter reading is going to be 1. Definitely is going to be 1. Definitely, yes. Is going to be 1. So I haven't done that. Moving on to the 16 volt. If the voltage are doubled, I'm just looking at, if I don't want to go through the stress of the calculation, mind you, if 8 volt is giving me 1 ampere and this has now doubled from 8 volt to 16 volt, then I think the ammeter reading should just double to somewhere around 2. But let's try to just look out for this. Okay, my inverse of my voltage now is going to be 1 over 16 volt. If I try to compute that from a calculator, 1 divided by 16, that's going to give me 0.0625 per volt. Now let me see graph for that. 0.0625 per volt. On my graph, what's that going to 0.06? Okay, this is 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. So that should be somewhere around. That should be somewhere around here. So if I try to trace that, out, so that should give me in between, and in between. If I trace that down, okay, using my extrapolated line, okay, that falls on 0.5. Yes, that falls on 0.5 per ampere. So I was told to look for the current. So the current is going to be 1 divided by 0.5 per amps. So that's going to give me 2.0 ampere. Exactly the prediction I gave before the start of the question. So that ends question 7. Okay, we move to question 8. As you can see on your screen, question 8 talks about determine the frequency F of the AC source from the formula F equals to 1 over 2 pi Lx. My L here is given as 0.024. Of course, I have my slope already. My pi, I was told to take that as 22 over 7. So I was told to calculate the frequency here. So the frequency here is something direct enough. 1 divided by 2. My pi, I'm taking that as 22 over 7. And my L is 0.024. And my slope is 0.125. Okay, 7 is going to move up. So my frequency is 7 divided by 2 times 22 times 0.024 times 0.125. Now trying to compute that, that's actually 53.03, but that can be approximated as 53.03. 0.0 hertz, because of course we're dealing with frequency here. So that is that on question 8. On question 9, we were told to talk about the precautions we are going to take here to get accurate results from this experiment. So we're looking at IX. So that's that about VII. Now talking about IX, we were told to state 2 precautions necessary if we were to perform this experiment as against when it is alternative to practical. So what are the precautions? The first thing, when you're dealing in electricity, because of your wires, your solenoid, as you can see in this experiment, you need to ensure tight connections and clean terminals. That's the first thing. Then the second thing is to avoid power loss error. I cannot overemphasize this. You want to take your reading, you're looking at your voltmeter, you're looking at your ammeter, look at where it is pointing to. Look at the graduation it is pointing to directly, not from the side, so that you can give precise readings. So you avoid power loss error when taking your reading on the ammeter and the voltmeter. Another thing is, if you look at the experiment was performed 5 times. It was repeated 5 times. The reason for that is so that we can get precise, we can get accurate values. So you ensure the readings are repeated so that you can get accurate mean values. Then lastly, you take note of 0 error. At one time in some of our videos, I had talked about 0 error. 0 error is this: I am using an instrument to take a measurement, but let's say in the case of the voltmeter now, it is not the arrow is not pointing at the 0 mark. Let's say you see some voltmeter or some ammeter, the pointer is off the 0 mark. So which means now if I use it for any measurement, it's going to give me a figure more than it should normally record. So what happens is that I have to take into consideration the 0 error. 0 error just simply means the instrument is giving a reading other than 0 when that instrument is not in use. So you take note of 0 error on the ammeter and voltmeter. Okay, now moving to question B. We were being asked for question B. It said, give a reason why a moving coil ammeter may not be suitable for measuring current in this experiment. In this experiment is about an alternating current. As you can see on your screen from the start of the question, you have a solenoid and then you have a variable low voltage AC supply, alternating current supply. So you cannot use a moving coil ammeter to measure your alternating current. So the circuit is an alternating circuit. Okay, what the circuit is an AC circuit. Thus, a moving coil ammeter cannot be used, as a moving coil ammeter is used to measure direct current in a DC, in a direct circuit. Okay, so what instruments can we use for this alternating current in this AC circuit? We can use a moving iron experiment. That is what we can use. Okay, on B2, we were being asked another question. The question states, define inductive reactance. Inductive reactance, XL, is the opposition offered by the inductor. If it were capacitive reactance, it's going to be by the capacitor, but in this case, it is by the inductor. Inductive reactance, XL, is the opposition by the inductor in an AC circuit to the flow of AC current. So you look at it, inductive reactance, something is going to oppose the flow of in the AC circuit, is going to oppose the flow of AC current. But what is going to do that is the inductor. That is why it is called inductive reactance. Also recall, SL, that's your inductive reactance, is low if the frequency is low, and your inductive reactance is high if the frequency is high. Also in this B2, question B2, we were told to write an expression for the reactance of the circuit. Write an expression for the reactance of the circuit. Now this is the expression XL equals to 2 pi FL. Recall how this works is 2 pi FL in question number VII, in question 8. In question VII, we were given an expression for the frequency F equals to 1 over 2 pi LX. We're given an expression like this. Okay, so what it means is that XL, if X should come here, XL equals to 1 over your X. So if X should come here, what you're going to have is X equals to 1 divided by 2 pi FL. 2 pi FL. So therefore, if I bring this here, what that means is 1 divided by 1 over, you can see that 1 over 2 pi FL. So what that means is my SL therefore will be, this is going to move up. So that's going to be 2 pi FL. And that is the reason why the expression for our inductive reactance is 2 pi FL. That way we have come to the end of this question. It's a 25-mark question and you cannot go wrong because this is a probable question for GCE alternative to practical. With that, we've come to the end of this edition. Remember, subscribe to this channel at 300 Plus Academy. Like, comment, tell us your view. Also, remember to visit 300plusacademy.com, where you can join various academic group and link up with your peers writing same exams so that you can exchange ideas, and as well you can DM us about topics you would want us to treat before your exam comes up. From myself and the team here at 300 Plus Academy, it's bye for now.